sampling, although that's not necessary, all the equations become much simpler. So we have, instead of a continuous signal, we have a set of values sampled at sampling points. Then we convert this signal by a kind of apparatus. So we get this signal, put it in, and we have some machine like a mill for minced meat. So we put the samples in, we have the handle, we put samples in, we turn the handle, and something goes out. And that what goes out, hopefully, is a set of complex numbers that describe the frequency components of that signal. So we have a DC component, then we have magnitudes of first harmonic, second harmonic, third harmonic. This is the real part of that minced meat got out of the machine. And of course we have phases. So we have a set of components with magnitude and phase shift at each relative frequency. Now the basic frequency is given by the interval we sample. So if we have 1 second time sampled, we get a 1 Hz component as the basic one. Depending on the number of samples, we get the number of higher frequency components, which then are spaced by 1 Hz. So we have F0, 2 times F0, 3 times F0, and vice versa. So this is something which is expected from the method. I'm not running deeply into mathematics, but I have to remind you that there are 2 important drawbacks. First, we have the Shannon-Kotelnikov theorem that says that in order to sample a periodic signal, we need to sample at least at twice the frequency of the signal. So what happens if we undersample the signal? Well, in fact, if this signal would be, for example, of this kind, with this sampling you would not reveal it. But something strange happens, and that's called mirroring. If you have a signal in frequency domain which has, for example, this bandwidth, but you sample it only with the number of samples or period of sampling relevant to this frequency window, you get a strange signal. You get the frequency signal mirrored, and what you in fact get is this. You get the correct result at those frequencies with extra signal content, which is not true. So those frequencies that are out of the band, still present in the signal, are mirrored at the edge back to the band. So if you, for example, have a signal from 0 to 300 Hz, and you apply a sampling which is enough for 200 Hz, so you would have a 400 Hz sampling frequency, you will get correctly the frequency content from 0 to 100 Hertz. And then you would get mixed the frequency components which belong to 100 to 200 Hertz and those that belong 200 to 300 Hertz. So you get a scrambled signal which is difficult to interpret, first, and second, those information would be mixed and you have no way how to decode it back. So if you undersample a signal and use a Fourier transform, you would get a complete nonsense. Now this is tricky because you possibly know that at nonlinearities mostly all harmonic components are present. So unless you provide a fine sampling, you will neglect some important parts of energy of the signal, and that would reflect somewhere to the spectrum. So this is the first point. You have to provide correct sampling. If you do not do that, you get garbage in your calculations. So this is the first property of sampling and therefore Fourier transform, the discrete Fourier transform of periodic signals. This is more or less widely known. Then there is a second property which is also important. So again, we have a set of samples in time domain. We apply it to a fast Fourier transform. We carry that out. We get out a set of complex numbers that describe magnitudes and phases of the respective frequency components. Now, a few minutes ago I told, well, okay, if I have a 1 second of samples in time, I have the first harmonic at 1 Hertz in the remaining signal, or I could get it. It could be 0 for certain numbers at the input, but anyway, I can get 1 Hertz. The second harmonic would be 2 Hertz, 3 Hertz, 4 Hertz. Now, each numeric approach has also some error. In the case that the signal that I have sampled is periodic and I have exactly sampled one period of the signal, then I will get really the value of the first harmonic or the content of the first harmonic in the input signal. But what if I have some signal for which I do not know the period? So I will sample it for some time and then throw it to fast Fourier transform and get some frequency components. Now, is there any estimation for the maximum error that could happen in this case? Well, mathematicians have provided us with an estimation of the error, of the maximum error. And the maximum error is 100%. That's not that bad. It just means that if I do not know the period of the signal or the basic frequency of that signal, and I just blindly put it into a Fourier transform, then I get some frequency components. But unfortunately, it might happen that I have, say, 1 volt at 1 Hertz, but the reality could be anything from 0 to 2. Now there is a question whether I can somehow decrease this error. In the bad case, I do not know the basic frequency, so I do not know the correct time for sampling. And the reply is yes. If I oversample, so if I make 2 times more samples within the same slot, I will get a set of different components, and each of those frequency components would itself suffer from the maximum error of 100%. But if I average 2 together, so this combined error for the average would be only 50%. So if I make a 4 times more samples example and average 4 frequency components at the output as to the magnitude, I can get only 25% maximum error. Yes, that's a maximum error. If you are only slightly wrong with the sampling time, the error would not be as high. But anyway, the important knowledge you should have is first that the situation that fast Fourier transform has produced some frequency component at a given frequency from sampled data does not mean that the signal contained any frequency like that. It is only reliable in the case that you have really sampled a periodic signal so that the sampling time matches with the time of one period or 7 periods of that signal. Otherwise, you get an additional error which could be up to 100%. So yes, if you have a frequency component produced like that in your calculations, you can be sure that there is not more than 2 times the amount you have obtained. But you are not sure that there is any frequency component there. And after those comments on fast Fourier transform, discrete fast Fourier transform, we can go on to a method which is called harmonic balance. Now that is something that I would have to describe a little bit more, and I will do it immediately. I am not returning back to questions because I have only repeated something you possibly know from mathematics. I have done it because it is important for today's problems. So now let's get again to an electric circuit. And let's try to get a good solution to a circuit which has some nonlinear components. Having an electric circuit, strictly speaking, there is no linear component at all. Once you are really interested in nonlinearities, and you do not have only a small weak signal at the first stages of an amplifier at the antenna reception, in fact, all elements like capacitors, inductors, resistors are somehow nonlinear. Once you measure it, let's say, 80 dB under the basic signal, you would find out that any of those elements is weakly nonlinear and produces some harmonic components, be it an inductor, be it a capacitor. But we are now trying to understand not weak nonlinearity. So let's say we have some circuit which has a lot of resistors, capacitors, and a few nonlinear elements like mixing diode or a transistor. In that case, wouldn't it be possible to somehow use all the stuff of linear circuit analysis to take off the burden of many differential equations? I mean, if you have there a lot of differential equations, it would be very slow and the numeric error would somehow accumulate. So if there are only a few nonlinear elements, wouldn't it be able to somehow treat nonlinear elements separately and the rest of the circuit calculate using known and nice properties of a linear system? And this is what is harmonic balance about. Now let's start this by explaining we have a circuit. This circuit contains both linear and nonlinear elements. Now imagine that we have a magic knife and we can somehow cut all nonlinearities out of the circuit and remove it to an extra box. And at the same time, this box would be connected back to the circuit by a set of wires. At low frequencies we could do it easily, but we have also magic wires that have no phase shift over them. In fact, we only think that's an experiment in our minds. The elements are still in the circuits, we only get them out to another box virtually. So we have separated the circuit into two parts. This is a linear part, and this is the nonlinear part. We have two parts, the linear one, the nonlinear one. All elements here are nonlinear, all elements here are purely linear. This part would be easily solved in frequency domain by many circuit simulators. That's peanuts. At any given frequency, we have good models for capacitors, inductors, resistors, coupled lines, I don't know what. This part is nonlinear, and for that description and solution, time domain method is ideal. So let us solve this part in time domain. Yes, and we have here those wires that are connecting all those elements. We have somehow cut off those nonlinear parts from here, and they are still connected by wires to the original place in the circuit. Now, what that does mean? Well, we have a set of wires with some currents, I1 to IN, and of course voltages. This is Vn, this is V1. Let's measure voltages against ground and currents as they are inside or flow through those wires. Now, the current within this wire could be seen in two or from two different standpoints. In fact, we can watch or treat the current as a set of harmonic currents with basis, twice the basis, 3 times the basis, as a Fourier transform of that current. So we can handle that in frequency domain like currents with F1, 2F1, 3F1, and of course DC. And that same holds for voltages. Now, from the other part of the world, we can describe the currents and voltages as well. But this time, those would be time-dependent values. That is, when sampling is applied, we would have V1 at 0 time and V1 at and delta t. Well, delta t is the time step. So we would have a set of samples for the voltages and currents here, and we would have a set of harmonic components just here. And there is something that could connect those two sheets of paper. And that something is called Fourier transform. So that we have some glue that can glue both two worlds together using Fourier transform. Now, in this way, it would be Fourier transform transforming time domain samples into frequency, and in the other direction it would be reverse or inverse Fourier transform. But anyway, that's the same mathematical algorithm inside. Well, this is all fine. We can quite easily handle those nonlinear parts of the circuit in time domain. We can quite easily handle the remaining and more abundant linear part of the circuit in frequency domain. We can transform the currents and voltages in between those two domains, but still we do not have a solution. Now, what would a solution that both has considered all linear analysis here and nonlinear analysis here, what would it mean? And that's what we call by harmonic balance. Now, I will describe it in this manner. Let's say we have an ingenious engineer who is designing the circuit. Now he comes, says, okay, I will have those transistors and diodes and nonlinearities here, those 75 other circuits elements over here. I have 4 currents and voltages in between those parts. Okay. Well, I think that, well, okay, the time behavior of all those signals would be this. And let's say he is in